enable or disable selected logic on that module, or to provide a constant for certain arithmetic operations. This completes our discussion of the electrical characteristics of the 5-4 gate. We will now take a look at how Cray Research uses Boolean equations in place of logic diagrams to represent AND functions. For the purposes of all future discussions, a parenthesized term in a Boolean equation indicates the inverted term. Parentheses were used in Boolean equations in place of overscores to simplify the printing or typing process. An overscore will be used to designate the inverted term in other than Boolean equations. A simple Boolean equation and its associated logic symbol are shown in the upper left-hand corner of the diagram. A0 equals B0 and C0. The AND symbol between B0 and C0 is not shown, but is assumed. To convert a Boolean equation to its logic symbol equivalent, draw an AND gate and assign the generated term, in this case A0, to the normal output. The inverted output will then be the opposite, not A0. The ANDed terms are then assigned to the inputs. Example 2 is similar, except that one of the inputs, not B0, is inverted. The same rules apply to example 3, although the results appear rather strange. Again, we assign the generated term, not A0, to the normal output, and the terms being ANDed to the inputs. The reason why inverted terms are sometimes assigned to the normal output will become clear later when we discuss OR conditions. The last example again follows the same rules. Although all of the examples shown require only a 2-input AND gate, remember that up to 5 are available for solving more complex equations. Now let's take a look at the rule for test pointing 5-4 gates. If there is a test point associated with a gate, the test point will be shown to the left of the Boolean equation. The test point may or may not be in parentheses. If it is not in parentheses, it is tied to the output of the gate with the normal term. If it is in parentheses, it is tied to the output of the gate with the inverted term. Test-pointed outputs may not be used to drive loads. In example 1, test point A20 is in parentheses and therefore is tied to the output of the gate with the inverted term. In example 2, test point A20 is not in parentheses and therefore is tied to the output of the gate with the normal term. Example 3 illustrates the point that the presence or absence of test point parenthesis determines whether it is tied to the normal or inverted term and not the normal or inverted output of the gate. In this case, A20 is in parenthesis and therefore is tied to the output with the inverted term and not to the inverted output of the gate. Example 4 illustrates the same point. Do not continue with this course until you thoroughly understand the Boolean and test point concepts just presented. You may want to turn off the tape unit and review the examples just covered in your workbook. Turn the tape unit back on when you're finished. Even though the Cray one only uses AND gates, it is often useful and sometimes absolutely necessary to perform logical OR operations. In order to perform an OR operation using AND gates, the OR equation must be converted to an AND function. This is done by using De Morgan's theorem. The conversion from OR to AND is usually done by the design engineer, and what appears in the Boolean is the already converted expression. The conversion process is, however, worthwhile covering. It enables one to recognize when an OR operation is intended, even though the associated Boolean equation is expressed as an AND. Let's start out with the Boolean equation A0 equals B0 or C0 or D0 or E0 and apply De Morgan's theorem in converting to an AND function. Step 1 of De Morgan's theorem says that both sides of the equation should be negated. This would produce not A0 equals B0 or C0 or D0 or E0 not. Step 2 says that we can break the line in the second half of the equation if we change the sign. That operation would produce not A0 equals not B0 and not C0 and not D0 and not E0, which can now be solved using an AND gate. This is shown in step 3. A0, which is located on the inverted output of the gate, will go to a 1 if B0 or C0 or D0 or E0 is equal to 1. Keep in mind that when you see a Boolean equation with an inverted result, it is actually meant to solve an OR function, as in the case of not A0 equals not B0 and not C0 and not D0 and not E0. When that equation is solved using an AND gate, it also results in an inverted term being assigned to the normal output. If a test point is designated, it is assigned just as it was in previous examples. A20 is in parenthesis and so is tied to the output with the inverted term. The last and most complex Boolean equation associated with the AND gate involves both an AND and an OR function. The example shown is A0 equals B0 and C0 or D0 and E0. If OR gates were available, the logical solution to that equation would be rather simple: two AND gates feeding an OR gate. Without an OR gate, De Morgan's theorem must be used. First, both sides of the equation are negated, producing not A0 equals B0 and C0 or D0 and E0 not. The next step is to break the line over the OR symbol and change the symbol to AND. All logical operations now involve only AND functions, and we can solve the equation using AND gates. B0 and C0 are ANDed together and inverted by using the inverted output. The same is true of D0 and E0. The inverted outputs are then ANDed together to produce the final result. A0 on the inverted output of the final AND gate is the logical solution to the original equation on top of the diagram. The test point in the original equation is not in parenthesis and therefore is tied to the normal term A0. That completes Unit 1 of this course. Stop the tape and review the material in the workbook, including the key points. Work the exercise and compare your results with those given. Review the tape again if necessary. Turn the tape player back on when you are finished. In Unit 2, we're going to describe the generation of the master clock and its fan out to each Cray 1 module. The master clock ensures total system synchronization. There are 4 selectable clock speeds controlled by a switch on the power distribution unit. 3 speeds, fast, slow, and super slow, are used for margin checking. The normal speed is used under normal running conditions. Several variations of the master clock have evolved over the years in an effort to improve its stability. A brief description of those variations follows.